So we've all seen a single robot arm do some pretty amazing things, right? But what happens when you bring a second arm into the picture? Well, it's not just twice as hard. No, it's a completely different ballgame. Today, we're going to break down the really elegant engineering that lets two robot arms work together in perfect harmony.
So let's just get right to the core question. If you already know how to control one arm, why can't you just, run the same code twice on two different arms? What makes this duet so much harder than two separate solo performances?
And wow, this slide just lays it all out, doesn't it? A single arm? It's pretty straightforward. It just has to worry about its own position and orientation. But add that second arm, and suddenly you have this whole list of new problems. They can't crash into each other, they have to start and stop at the exact same time, and then there's this really subtle, tricky new problem. How do you keep them from accidentally crushing or ripping apart the very object they're trying to hold? Let's unpack how engineers figured this out.
Okay, first things first. How do you get two robots to even agree on what they're doing? It all starts by giving them a single, shared point of view.
And the answer is it's so elegant. It's a concept called the object-centric frame. I want you to think of it like an invisible coordinate system that's literally glued to the object they're holding. So instead of each arm thinking, where do I need to go? They both start thinking, where does the object need to go? It's almost like giving them a shared brain.
So here's the magic. We basically stop planning for the individual arms altogether. We just define where each gripper should be in relation to the object itself. Then, all we have to do is plan a path for the object, and the target positions for both arms get calculated automatically. It just simplifies the whole high-level planning problem immensely.
Okay, so now the arms have a shared goal. That's great. But moving together still requires the right kind of choreography. So let's look at the 3 different dance styles these robots use to coordinate their movements. Now, what's really fascinating here is how they switch between different strategies. When they're just approaching an object, they use a synchronized mode to make sure they get there at the same time. For some tasks, it might make sense to have a master arm that leads and a slave arm that just follows along. But for the really cooperative stuff, like carrying a box together, they switch to a symmetric mode where they are both equal partners, just following the object's lead. But the second both arms grab onto that same object, we hit what is maybe the most unique and difficult challenge in this entire process, managing the forces between them. And yeah, this is the million-dollar question, right? Think about it. If one arm pushes just a tiny bit harder than the other, or if their control loops are off by even a millisecond, they could instantly create these huge internal forces and just crush the box they're trying to move. You can see the danger right there on the left. Any unbalanced force is totally wasted. It's just destructive stress. The solution, over on the right, is this brilliant control strategy that makes sure any of those unwanted forces just naturally cancel themselves out. And the solution is this amazing concept called dual impedance control. I want you to imagine that each arm's controller is acting like a virtual spring. Now here's the kicker. If you make those two virtual springs absolutely identical, same stiffness, same damping, the system just becomes naturally balanced. If one arm pushes a millimeter too far, the other arm's spring provides an equal and opposite pushback. They automatically cancel each other out without needing a bunch of complicated force sensors. It is such a beautifully simple fix to a massive problem. Of course, you don't want the force to be exactly 0. To make sure the box doesn't slip, the controllers are programmed to add a tiny intentional squeeze force, about 10 newtons, right along the axis between the two grippers. It's just enough to maintain a really firm grip. So we have our shared reference frame, we have our different coordination modes, and we have a slick way to manage internal forces. Now, let's see how a director brings all of these pieces together to perform a complete task, from pickup to put down. That director is something called a bimanual state machine, and you can just think of it as a step-by-step checklist or a script. It's a simple sequence that tells the arms exactly what to do and when to do it. It orchestrates the entire performance from the first approach to the final retreat, and it makes sure every single phase happens in exactly the right order. And here we can see some numbers from the actual pipeline in action. You can see how each phase is timed out. The carry phase, for instance, moves the object a full 30 centimeters in about 2 seconds, and it does it all while perfectly balancing those internal forces to keep the object completely safe and secure. And here's a really clever little detail from the simulation. To make sure they could focus purely on the high-level problem of arm coordination, the moment the arms grab the object, a virtual weld is activated. This basically simulates a perfect, unbreakable grip, so the researchers could worry about the big arm movements, not the nitty-gritty physics of finger friction.
So, after going through all of that, what are the big ideas? What are the most important principles we can take away from this incredibly cool and successful system?
You know, it really boils down to these three brilliant ideas. First, you have to create a shared goal, and you do that using the object-centric frame. Second, you use symmetric impedance to passively and just brilliantly solve that internal force problem. And third, you use a simple state machine to direct the entire complex ballet of actions. And the results of all this careful engineering? Well, you get a system that can pick up an object, carry it across a workspace, and place it down with a final positioning error of less than 1 centimeter. For such a dynamic task, that is a truly remarkable level of precision. And that leaves us with a pretty fascinating thought to end on. The principles that we've looked at today, shared goals, coordinated motion, balanced forces, these are really the fundamental building blocks for much, much larger systems. So if this is what just 2 arms can accomplish together, imagine the possibilities when we have entire teams of robots building, exploring, and creating together.